Should we start? All right, right on. Thank you for coming. This is Trends in Supporting Production Apache HBase Clusters. I'm Kevin Odell. This is John Shea. Who are we? John is a software engineer at Cloudera. He's also an HBase committer as well as PMC member, and he's the founder of Apache Flume. I am currently a systems engineer, and I'm an Apache HBase contributor. And before I was a systems engineer, I was the HBase support team lead. Quick question, how many people are using HBase in here? All right, so most everyone. So what is HBase? HBase is a reliable, column-oriented data store that provides consistent, low latency, random read and write access. HBase is designed to be fault tolerant and highly available. It'll also depend on the underlying systems to be as well. HBase keeps its fault tolerance by being able to serve regions from any region server, built-in HA with the masters, using Zookeeper quorums to make sure the region servers and the masters are up and running and doing what they're supposed to be doing, and relying on HDFS block replication for not only fault tolerance, but as well for performance with data locality. We're going to talk about trends in supporting Apache HBase. These numbers all come from our operations team and real-world tickets. So one of the big things we want to talk about is the environments that we saw 2 years ago versus last year. And that was the CDH3 era versus the CDH4 era. And we were seeing Red Hat 5 with ext3 partitions, Java 1.6, 1.3, and one of the things that we saw from the move from 1.3 or 6.13 to .31 is there was some weird pause JVM issues, as well as some out of memory errors that it would just out of memory and you wouldn't see any kind of error messaging. The machines have gotten larger and more powerful, so you see 10 to 15 disks versus 4 to 8 disks. RAM's essentially doubled, and the core count has also gone up as well. CDH3 was based on HBase.90 and Hadoop .20, and our CDH4 distribution is .92 or .94, depending on which version you're on, and it runs on Hadoop 2.0. So if you flash back to 2 years ago, you can see we have a few main categories we want to talk about. First is patch bugs, which is where we had to either deliver a patch on the fly or it was fixed in the next version. We had operation workaround, which covered about 72% of our total ticket count. That was anything from a misconfiguration to schema design or tuning issue, or HBase was inconsistent. We had to use HBCK to resolve it. Then the next category is network, hardware or operating system, really any underlying system issue that covers for that category. And you can see that was only a small portion of the ticket. So comparing the data between the two, we added a new category for documentation, and that's anything from a spelling error to incorrect instructions to missing features for documentation. The patch category remained about the same, going up 2%. You can see that our workaround, we combined from config to HBCK into one category, and it was literally cut in half from 72% to 36%. And our underlying subsystems is at 42%, and that's the trend that we want to see going forward. Taking a look at the new data, the majority of the customers had upgraded to CDH4. We have more customers, but our number of incidents and support stayed about the same for HBase, which is a good sign. And we cut in half our largest trouble spot. Now we see the larger number of issues being with the subsystem, which is actually a good thing. So I'm going to talk about some of the operations challenges we ran into while supporting these clusters. So the three main pain points I want to talk about is the underlying subsystem, our upgrades, as well as our configuration. So if you, who here actually runs a Hadoop cluster? So I'm sure all of you are very familiar with the leap second issue that happened. And that was where the Linux system had to add a second to the clock to catch up. and this caused anything with mutexes to go crazy and spike at 100% CPU, which is exactly what Java does. Also, Linux moved to using something called transparent huge pages, which is now in the file system rather than relying on the application layer to create memory pages over 4K. They do it in the operating system. And that caused issues with the defrag of that memory to cause spikes in memory usage as well as CPU usage. And then we ran into some bad 10 gig Ethernet firmware with some of the more cutting edge customers running in 10 gig environments. One of the things we added in is from Cloud Error Manager. It's the system host checker. I don't know if you guys can read that, but it does a check of the underlying host system, and it flagged on two things. One is the fact that we had processes that were still on with check config, so if we did a reboot, the operating system would start them before Cloud Error Manager had a chance. And the other one is a flag where it actually checks to make sure that transparent huge pages, the defrag is not enabled, and if it is, it lets you know and how to turn it off. So from our upgrade issues, we had old edits logs, which were .recovered edits that had been left behind and weren't properly cleaned up. And whenever you would run an HBCK run, you would see what would appear to be orphaned regions, but there wasn't actually anything in there. So we filed a JIRA to clear those up. We also ran into zero-length hlogs, which turns out to be an HDFS issue, where we have a bad ending to the file and it presents itself with zero length, which caused HBase to not be able to start up. Bad region references. In .90, we were a little sloppy with our splitting. We've since tightened that up, but we would have lingering reference files sitting around that we would have to clean up. And then invalid H file is a really interesting one. It's our Heisenberg bug. We were never actually able to reproduce this internally. It was just, we ended up having to find the H file using the H file tool and remove the offending H file from HBase. So one of the things we've done for upgrade assistance is we moved to parcels, which is essentially a unified tarball. It helps simplify the distribution. It also allows for a flexibility of install location to put all of your services in one place. And then side-by-side installs for rolling upgrades. And from an upgrade standpoint, we've added in rolling upgrades to our Cloud Error Manager, which does hot fixes or for minor version upgrades. As the wire compatibility comes downstream for HBase, we're hoping this will also translate into major upgrades as well. We've internally done automated tests for upgrade and compatibility to make sure that these issues are ferreted out before we start doing upgrades. So the configuration feature issues that we ran into, one of the big ones was continuous bulk loads. And bulk loads were originally designed to kind of bootstrap the system into doing a MapReduce job and loading your HBase table. But you could also keep running MapReduce jobs and loading them in. And John's going to talk further about how that affects compactions in his section. But what we did with most of our customers was change the way they were doing things and tune their cluster to optimize for a put-related workload. Region tuning is another thing that we saw. And that's, we updated the defaults in HBase and as well as in Cloud Error Manager. GC tuning, I don't know if you've ever tried to run a heap with larger than 16 gigs without any kind of garbage collection tuning in HBase. It just doesn't work. You're going to start timing out and having what we call Juliet pauses. So we built that into our subsystem as well. Balancer was a very interesting issue. In .90, it was based on region server. So we balanced the regions per region server as opposed to per table. So what would happen as you shut down for maintenance or for upgrades, regions would transition around, and then you would end up with one region server that had 90% of the regions for a specific table. So when you go to access that table, you would just be hammering one region server and essentially eliminating the distributed nature of HBase. So that was a manual process. And before that, you would have to pull down what regions lived where, put them in an Excel spreadsheet to visualize it. There's a great tool out there if you haven't seen it. It's called Hannibal. I highly recommend it. It gives you a visualization of how your regions are laid out and how your regions are sized as well. And then bad schema is just trial and error. And so one of the things that we did there, and John's going to talk more about how we're trying to do that in the community, and that is through frameworks and just education, really, is about all you can do there. So one thing we found is Cloud Error Manager helps the sanity checks on the configuration, the wizard-based installs and setup, the rolling upgrades, and as well as the wizard-based backup and recovery strategies. Here's a quick screen cap of what the configuration page looks like if you haven't seen it. It's a nice GUI interface that allows you to set all your configurations for your nodes and roll those out so you don't have any discrepancies between what your configs are per node. From a support wish list to engineering, improved ergonomics. So better configurations and guardrails. So one of the things that we saw a lot was either fat fingering a config. So rather than having a 128 meg flush size, you would have a 12 meg flush size. Or rather than a gig region server, 100 meg region servers. And that's not ideal. The merge process is not fun. Changing the flush size requires downtime. So we'd rather have HBase just alert and kind of say, hey, you know, I'm sorry, Dave, I can't let you do that. And that way it's smarter and just makes it easier for everyone. And then improved error messaging. I have spent hours looking through logs, and a lot of them aren't necessary. We want to improve the signal to noise ratio so that you can kind of get to the heart of what's going on. So that's from anywhere from moving some stuff from info to debug and then cleaning up some messages. And more improved ops tooling and framework for app development, which would make development along HBase easier and bring more people into the project. So the good news is all bug fixes go in Apache before they go into CDH, but HBase is maturing. And we've seen that from the higher percentage of issues in the underlying subsystem. So now the cases have moved from my region server has crashed to HBase seems to be running slow. Is there a way we can speed this up and do more? And then a similar amount of cases caused by bugs. And we're getting better. So we have the lower percentage of incidents managed by workarounds, as well as more customers running HBase with a similar volume of cases. And then tools in place to help support. HBCK, I can't speak highly enough of the work that went into that. We went from days to fix an inconsistent cluster by hand to fixing it in hours. Cloud Error Manager helps with the rolling out, the configuration, the monitoring, and the default configurations that have gone into HBase itself to raise it up to be more in tune with the way hardware's growing as well. But we can still do better. So right now I'm going to turn it over to John, and he's going to talk about where we are and where we're going.
Thanks a lot, Kevin. Forward and back. Okay, great. So hi, I'm John. I'm on the development team at Cloudera working on HBase. I've been working on HBase for over 2 years now, committer, et cetera, blah, blah, blah. So I'm going to talk about some of the things we're doing to improve HBase from the engineering side of the table. It's sticky. There you go. So this is a slide that was shown at HBaseCon 2 weeks ago, but it's basically showing that the amount of code that's in the HBase system between 2011 and 2012, and between 2012 and 2013 has grown significantly. So there's been a lot more effort, a lot more people involved in the project, and a lot more things getting fixed and added to the HBase system this year compared to the year previous. This is actually a really good sign. That means we have many, many more users, many more people who actually are depending on the software, and many more people who are finding and reporting bugs and fixing them, as well as just using the system. And I think if that trend continues, we'll continue growing, which is great. So my part of the talk, I'm going to talk about some of the things that we've done to improve support for future versions of HBase. So the version that's going to come out soon, hopefully this fall, is going to be called HBase 96. And right now we're in a dev mode, so we have a 95 release, which is kind of a preview release. And basically I'm going to talk about improvements in 3 categories. Improvements in usability, improvements in reliability, and improvements in predictability of the HBase system. And this is primarily attacking the places where there are bugs and the places where workarounds had to be used in previous versions. So first, I'll start talking about how we're going to do some improvements to the usability of the HBase system. So as we can see, administering HBase has not always been the easiest task, right? It's difficult for a couple reasons, primarily because it's difficult to see what's going on inside of the system. And what we found over time is that it's easy to make bad decisions early on that you don't have to pay for until you've scaled up. So what are the things that we can do, and what are some of the features that we can add to make this easier and prevent yourself from making these kinds of mistakes in the first place? Well, first, we revamped the metric system. We've added a mechanism called htrace. And one of the things that's coming outside of HBase is a community of frameworks and things that are going to help simplify the tasks of building applications on top of HBase. So the metric system is basically revamped, so now it's consistent. The different metrics within HBase kind of grew organically, so things weren't really named in regular patterns. And in the next version of HBase, all the names for all the different metrics have been regularized, and they've been converted to the Hadoop 2 metrics framework, which allows all the metrics to be sent to your favorite metrics viewing tool, such as Cloudera Manager, Ganglia, OpenTSDB, Hannibal is one that Kevin mentioned, and there's a handful of others as well, but these are probably the most popular ones, and it's really good for you to be able to get both more metrics and finer grained metrics about your tables and about your HBase information visible to your operators. So that's a major improvement in this upcoming version. A nice little side note is that when we redid the metrics, we actually got a performance boost because there was some performance contention. There's some contention in the metrics, and we kind of were able to get rid of that problem while we redid the metric system. Something that is more for developers is a subsystem called htrace. And the problem we're trying to solve with htrace is trying to figure out where time is being spent within HBase and its underlying systems. So this is actually a tracing system that is baked into, potentially baked into HBase, and is also threaded through HDFS and all the other different processes involved in having an HBase cluster work. So the idea here is that you would be able to trace an RPC call, see it go from the master to a region server, which are parts of HBase, and then go down to the data node or the name node and basically get an idea of where time is being tracked in all these different calls. So logically, one RPC call from a client, you'll be able to see where time is being spent on all the different machines involved in making that happen. This is inspired by a paper called Google's Dapper, and it's basically very similar in design. Now, this isn't fully ready for an average admin today. It's primarily used by developers and can be used by developers, but we'll be fleshing this out more in this future version and probably point releases afterwards as well. It's actually really important for another part of the talk when we start talking about improving reliability in the system. The big place that everybody is going to have problems, and everybody has had problems, if you went to HBaseCon, you'll have gone to the case studies track, and basically everybody said, the first schema we came up with for HBase wasn't quite right. And it's really because, picking a schema requires some in-depth knowledge about HBase and its architecture and how to take advantage of the power that it provides. And the interesting thing is a lot of these problems actually don't show up until you start scaling up and start ingesting lots of, trying to do a lot more data ingestion or trying to do a lot more data analysis once you've scaled. So the question I'm trying to answer here is, what can we do to try to make the schema design decisions easier? And how can we reduce the amount of expertise required to pick effective and good schemas for the kinds of workloads that you're trying to do with your applications? So, again, as a developer, I love knobs. There's tons of knobs that you can turn. But as someone who's trying to build an application on top of it, there's just kind of too many choices and too much you really have to learn to take advantage of all of it. And what's worse is some of these things are really expensive to fix after the fact. So this is actually a slide that I usually give. This is a summary slide, actually, that I usually give when I talk about designing schemas for HBase. These are basically some of the standard tricks that you have to know as an HBase application developer to take advantage of the row key structure and some of the region structure to get proper sharding and to get proper performance and proper sorting of all your data for particular kinds of workload. You have to take advantage of the lexicographical sort by padding your numeric values. You want to reverse values so that things come out sorted in a way that's going to be most efficient. You have composite row keys that combine multiple things that actually percolate all the way up to the application. Really what it boils down to is you have to know a lot of details, And like the best thing that we have now is this flourishing of new frameworks that are built on top of HBase to help you with your schema design and help you take care of a lot of these mechanical problems that everybody has to solve. Typing, picking how you're going to search through things. And I basically boil it down into two categories, right? These frameworks are here to essentially encapsulate a lot of these tricks and turn it into something that an application developer is more used to thinking about, right? So one category is a SQL skin. So this is embodied by projects like Apache Drill, Salesforce's Phoenix, and Cloudera Impala. And then there's also emerging application frameworks that help you build entity-centric applications like Kiji and this other toolkit called the Cloudera Developers Kit that's recently come out. And I think this is actually going to be the long-term solution for application developers to simplify the process of building, let's say, 80% of the applications on top of HBase. So, those are the things that are kind of application developer and user-centric. Next, I'm going to talk about some of the internal improvements that we've added to HBase and that we're working on in HBase to make it easier from an operator's point of view. This is primarily focused on reliability. So let me define two terms first. First, there's reliability. And then this is something that HBase has been good at for quite a bit now. It's the ability to recover from failures within the system without losing any data. I think HBase is actually very, very good at not losing data in the system once it's been put in. However, what we haven't been as good at in the past is recovering quickly from these failures without losing any data. So last year's talk, if you came to it, I was talking about all these things that we did to improve the recovery time in the case of a failure. A lot of these things are now in place. We've seen numbers now where this has helped the situation. We have more techniques being done by folks at Cloudera and folks in the community to help make this problem even easier and even less painful. So what are we trying to measure? We're measuring this metric called mean time to recovery, MTTR. MTTR is basically the average time required to automatically recover from a failure within the system. So you have a cluster of machines, one of them goes down. How do you make sure that that data that that server was serving is back up and able to accept reads or accept writes? We break this down into three categories. The time it takes to detect a problem. The system has to figure out that something is wrong. The time it takes to repair a problem. Once we know there's a problem, how do we get ourselves out of that problem? And then notification time. Once the problem's been fixed, how does the client know that the data is ready and it can actually start doing the reads and writes again? So this htrace infrastructure that I mentioned before is actually really helpful because it helps us see where the time is being spent. So in some of our internal builds, we've instrumented the recovery paths to see how much time is being spent in which places in order to figure out which places we need to focus on more and can get the best improvement in MTTR. So, there's three places that take a lot of time. There's three places we can improve. We can start by reducing the amount of time it takes to detect a problem, right? So, a couple features that are introduced in the newest version of HBase that's currently under development in the dev release, the 95 version, is proactive notification of master failures and proactive notification of region server failures. Basically, what this means is if you kill or kill-9 one of these processes, there's a watchdog that will tell the master, hey, you need to go clean this stuff up. It used to be 30 seconds or 180 seconds before any action would be taken, potentially. Now, there's one case that those things don't take care of. This is the case when the wire gets cut in the network or the power gets completely pulled. And there have been techniques talked about at HBaseCon by a fellow named Benoit for fast server failover in the hardware switches. Basically, this is taking advantage of the level 2 ARP packets, and when it detects that a node's not responding, the switch will actually masquerade as the dead host and send TCP close commands to any open connection. Basically giving that notification time that used to depend on a TCP timeout into something that the switch can detect and proactively send notification about. So what we've done is we've taken the time to detect from something kind of big to something smaller. So what's the next step? Well, the next step is to reduce recovery time. And the main thing that reduced the recovery time necessary in HBase in the face of a crash is distributed log splitting. And this was a feature that was introduced in HBase 92. So this has been in production in CDH4 for a very long time and has been a huge boon. Basically, Prior to this feature, it could take a full cluster power down, full cluster power cycling could take hours to recover from. But now we're down to on the order of minutes, maybe an hour at the most, because it basically distributes all the work across all the nodes in the machine, all the nodes in the cluster. A new feature that's being added and being hardened right now is called distributed log replay. And basically this cuts the time that it takes for this log splitting, this log recovery in half essentially, by saving one pass of I/O. Related to it is a feature called fast write recovery. And what fast write recovery basically says is once I've detected that this region is down, this data that I'm serving is down, I'm going to assign it somewhere else. And because in HBase, writes are oblivious to reads, you don't have to read anything to do writes, it'll start accepting the writes right away. And this is actually really good for metrics collecting use cases and other places where you want to be able to constantly ingest data. You should be able to get back up in seconds. Related to that is a feature that we're going to call pristine read recovery. So reads, the reason we have to do recovery is to make sure that when you ask for a value, we give you the correct value, the most up-to-date value. And when there's a failure, we basically have to replay this log to figure out what the correct value is. If we can assert that there have been no edits to that particular region, that particular shard, then we can say, hey, you can go right back up and you can start serving your values right away because we know you haven't been modified. So that's a feature that probably is not going to make 95 and 96 in the first version, but it might make some of the later versions. Yeah, so we've knocked down the repair time from something big to something smaller. That's always good. So what's left? Well, it's the third thing. It's reducing the notification time, right? So the things that we're doing here, we've added a notification. So the idea here is that once all of the server-side things have been fixed, the client is actually sitting there polling periodically, exponential back off, to figure out whether the values are good again. And maybe you've backed off a couple times and you're waiting 16 seconds. Instead of waiting for that 16 seconds to elapse with the client before you try again, the servers will basically send a notification to the client saying, hey, things are back up, you should try this thing again now. So you can save a whole bunch of time there as well. One of the things we're also talking about is rewriting the HBase client to be asynchronous. And these notifications might be easier to pass along with that as well. So, notification time big, notification time smaller. Right? So the blue line is kind of how long, a representation of how long it used to take to recover. And our goal here has been shrinking the time it takes to recover from a failure. And I think with the set of features that we have, we're going to take it down from hours to minutes, hopefully down to seconds in most of the cases. All right, so that's recovering from failures. The next thing I want to talk about is predictability. And what I mean by predictability is, I want ideally to have few outliers. I want to have performance that's very regular. And what can I do? And what are some of the problems that cause these irregularities in performance, throughput, or latency? So we saw this slide before, reliable, highly available. We're adding another category, which is latency tolerant. And this is the ability to perform and recover in a predictable amount of time without having to lose any data, right? So we want our throughputs to remain constant as much as possible, and we want our latencies to remain constant as much as possible with few 99.9% outliers. So historically, there have been three major causes of performance fluctuations. There's been compactions, there's been garbage collections, and locality loss. I only have enough time to talk about one, so I'm going to talk about compaction because this is one that hit a handful of our customers, and we've actually added some things to make it better for them. Yeah. So who knows what a compaction is? Yeah, everybody, great. So I think the simplest way I can boil down a compaction is it is a process that rewrites data to be highly read optimized. It makes the read layout more efficient over time. What it does is, over time as you write data to HBase, you drop little files called H files through this process called a flush. And every time you add a new file, you have to incur more I/O to do a read. By compacting files together, we reduce the number of seeks because we only have to look up one file. We also thus improve the random read performance, and we also are able to get rid of data that has been marked deleted or has been aged off because it's no longer relevant. And when these compaction algorithms were designed, we had this assumption. We had the assumption that everyone was doing good HBase key design and doing their schemas and their writes in a way that uniformly distributed writes throughout the cluster and throughout the regions, throughout all the different places within a region. But what we've seen emerge is a couple different kinds of workloads that have been trying this initial assertion. So the one I'm going to talk about is a continuous bulk load workload. Basically, I'll describe it in the next slide. So, traditionally, a workload with puts will distribute data throughout the cluster, and in a particular region. So each one of these little cartoons actually represents the files within a region. We would periodically flush a file that's relatively small, say 64 megabytes, 128 megabytes, and then the region has to make this decision. Am I going to do something called a minor compaction, or am I going to do something called a major compaction? Major compactions are expensive because they take all the files and they squish them all together into one Uber file. Once you're done with this, you only have to do seeks on one file, so you get a lot of performance benefit, but it can be potentially expensive to rewrite your data, all of your data, essentially. You can also do a minor compaction, which takes a subset of the files, and there's a constraint where the subset of files has to be adjacent to each other. They have to be next to each other. Maybe if you squish a whole bunch of small files together into one medium-sized file, you'll get performance benefit there. And then later on, you can push off the major compactions for later. So on the left, you see kind of the first choice. There's a new region that shows up all the way on the right. And we've reached the threshold where we have to do a compaction. And we look at it and say, oh, well, these four are basically within the same level. They roughly have the same amount of data. And it doesn't have to include the big region on the left. I just am including the little ones on the right. So I'm going to choose to do a minor compaction and squish them together. And now I have two kind of medium-sized H files next to each other. And then eventually you do this again, and you end up having a bunch of medium-sized H files next to each other. After a while, you might get to the place where all you have are these medium files, and you need to do this compaction decision. If you include, if the oldest file is included in the compaction, it'll essentially decide, oh, I need to include all of them, and I'm going to do a major compaction, squish them all together, and have one big file. So the important assumption here is these files are kind of being built up kind of like the towers of Hanoi. The biggest thing is always on the bottom, and we're mostly compacting the smallest files. But we have the assumption that all the newer files are smaller. Bulk load changes the story because when things get added via bulk load, we're actually just loading these files directly into HBase. And as Kevin said, it's intended for bootstrapping, but when you're doing this frequently, you're adding lots of small files to the oldest section. And if you use the original algorithm, you'll add a bunch of small files to the left. It'll see that all these are about the same level. Let's do a major compaction because we included the oldest one. And what ends up happening is you always end up doing major compactions. You have this large region at the end, and you keep on making that large region larger and larger and larger. And it's very inefficient because you're essentially in a state called the compaction storm. And you're constantly rewriting files that shouldn't have to be rewritten all the time. So we've added a feature called an exploring compactor, which is a smarter way of doing minor compactions. And it chooses to do minor compactions based on reducing the number of files with the least amount of I/O. We still have the constraint where files have to be next to each other. But in this particular situation, you can see we had a bunch of bulk loaded files on the left, a bunch of flushed files on the right. Instead of compacting all of them, we'll pick either the option on the left where we squish all the bulk loaded files together, or squish all the flushed files together, and have more minor compactions, which is more manageable in the long run. So that's kind of my summary of of some of the things we're including predictability. There's going to be many more things, and we're constantly trying to improve that predictability, and we're constantly trying to improve the performance and the predictability of HBase's gets and puts. So in conclusion, here's kind of the summary slide for the support tickets, the comparison between 2011 and 2012. I think the key takeaway is that more of the problems seem to be due to underlying systems, and that HBase seems to be getting more robust. There's fewer problems due to HBase for Hadoop, and some of these are more just because of the upgrades of the underlying components. We're improving our testing to avoid some of these patching situations, and the tooling and development that we're working on is hopefully going to reduce the number of situations where workarounds are necessary. This is probably really hard to read, but the high-level point, it's kind of a summary of where all these different features I talked about have come in, or will come in, or likely come in. Basically, the idea is that back in the 90 era, you probably needed to have a HBase committer on staff to do a good job and build a successful HBase application. In the 90-92 era, there's a lot more information out there. It's a little bit easier to administer, so you probably need someone with some HBase ops experience to be successful to run an HBase cluster. I think today, in the version that's going to come out, we're lowering that bar even more with the frameworks that are coming out there and the more tooling. So someone who's got experience administering clusters or distributed systems should have a very good chance at being very successful at this. And then, hopefully with the next version, Nirvana, everything, unicorns and rainbows, right? I think the other thing that's important is that, continuing on the theme from last year's talk, basically the 90 version, it would potentially take you hours to recover from failures. In the 92 and 94 version, it takes minutes. In the version that's going to come out, 95/96, it will be seconds for writes and maybe tens of seconds or minutes for the reads. And in the version afterwards, when we have the pristine read recovery in place, it should be seconds for reads, writes, for many read situations and all the write situations. Anyway, so that's all that we have. I'm John, this is Kevin. If you have any questions, please stand up to the mics and feel free to ask. Thank you. Actually, you guys are first over there.
Okay, the hotspot guys say that the G1 collector is supposed to address the problem of lots of cores and big RAM. Are you finding it working for you or not? G1.
Yeah, there's not a lot of testing behind G1 right now, but from what I've seen internally is G1's really good with larger heaps, but not quite for HBase because of the way it churns. G1's just not quite there yet.
I haven't heard you talk about configuration changes. I'm particularly interested in the dependence on the host name for nodes identifying themselves. I mean, we have a situation where we have multiple statically configured LANs per node, and I want HBase to identify itself by something that's not identified with the host name. Is that something that's going to be addressed?
Do you want this one?
If you want to talk about the RPC binding, that's...
Yeah, so there are a couple options that you can twiddle the RPC bindings. This actually does come in to play as a problem with some features that we've actually seen in the field. I know we support some boxes that have dual homing, which is a little bit different than the situation you're talking about. I think it's something that in general we haven't done a great job with in the Hadoop community, in the HBase community. If you can chat with us afterwards, we'll get more specific details and we'll try to fix that problem.
All right. So in 92 and 94, is it like a snapshot is not in 94 available?
So snapshots is a feature that was backported to the most recent versions of 94. It's also included in CDH 4.2 and 4.3, which include a version of 94.
Mm-hmm.
So yeah, the snapshotting feature is in the more recent versions.
Mm-hmm. And what about HA? Like if you have two master nodes, and will it be like client has to do configuration differently than you have a single master node?
No, so if you're referring specifically to HBase HA, that's been in there for a very long time, and it's actually really painless with HBase. You spin up the nodes, they check into Zookeeper, and Zookeeper manages who's the master. The client actually rarely ever talks to the HBase master.
Are you talking about HBase HA or HDFS HA?
HDFS HA also, because of MapReduce comes into the picture.
So HDFS HA is actually, there is some It's tricky to set up manually. I tend to, when I spin up clusters, I just use Cloud Area Manager to spin them up for me.
Yeah.
And I spin them up with all the HA options on, and it sets up all the stuff for HBase.
Yeah.
It's essentially a different path, right? There's just a special name for the view for the HA part that allows you to pick between which name node, resolve that at runtime.
Yeah, and the one thing I'd mention if you're going to set up HA for HDFS is be aware that the zookeeper does store the current name node URI in the Z nodes. So you are going to have to go in and clear out the split logs data or your HBase won't start.
So let's say if you're using Cloud Area Manager and everything is through Cloud Area Manager, so does client can understand dynamically like the name node failover from master, like active standby you have, correct? And standby becomes active. Does client have to be changed, or it automatically determines there is a change in the HDFS, HA or HBase HK?
So the client doesn't know because it uses a namespace instead of actual name node. So it speaks to a namespace which HDFS handles itself.
All right, that's the last question we can take.
Okay,
We'll be around, and we'll probably head over to the Cloudera booth if you want to ask us more questions. We'll stick around here for a little bit as well. Thank you very much for coming.